purlins are basically a flexural member in which transverse loads comes into picture. In case of purlin, the moments from both the axes come into picture. As a result, purlins are need to be designed for biaxial moment. So, we need to check the bending moment carrying capacity in both the means against both the axes, and then we have to check the interaction formula. So, that the purlin is designed, and these purlins are basically connects the truss members in the roof structure to support the roof sheets and other materials, and these purlins are placed on the rafter. Let me show a picture through which we can see that if this is a roof truss, then we can see that trusses are connected with these purlin members. These are the purlin members, and these purlin members are placed on the rafter. This members is called rafter, and the between two truss members purlins are connected, and if you see these purlins are inclined means are placed in an inclined position, and these purlin sections are basically means whatever we use is channel section or angle section, because load is quite less, and as a result we generally provide some lighter section like channel or angle section. Sometimes also we use I section also. Now, we will see how to place the channel section or how to place the angle sections in a inclined roof, that we will see, which is the recommended configuration. So, now if this rafter is like this, which is slanted, say this is a section, say I sections we have a rafter, then the if we use channel sections, we can use in this way, not in the reverse way. So, its flange will be towards up, right. So, this will be the axis, and similarly, if we use say now we have to connect this purlin to rafter with some angle section in this direction. So, this is connected like this. So, here we can provide bolt or weld, and here we can provide bolt or weld. Then we can make the connection between rafter and the purlin. And if we use say for example, angle section, then angle section should be placed like this. Angle section should be placed like this, where it will be connected with another angle to the rafter through this, right. So, which is called cleat angle. So, this is called cleat angle, and this is rafter, this is purlin, and the load will be coming. One is the load which is the wind load on the roof. So, wind load we assume that it is normal to the roof, it acts, wind load acts normal to the roof, and the gravity load due to self weight and snow load or other sort of load are acting vertically downward, right. So, this is one load and another load is this. So, this is say H dash, the wind load which is coming perpendicular to the axis of the purlin, and the vertical load which is due to dead load and other snow load and other loads, dust load etc. So, that is vertically downward, say maybe we can write as P dash, right, and this we can use as UU axis, and this we can use along the direction, say this is VV axis, right. This is the VV, and in fact, this will go through this means CG of this VV axis. right. Similarly, here it will be like this, somewhere here like this UU and VV. Similarly, I sections also we can provide. I sections maybe we can provide like this, say for example, this is an I section which we can provide, where UU axis will be this and VV axis will be this, and in case of I sections the angles will be provided, the cleat angles will be provided with the help of packing. Say for example, this we can provide like this, and this will be packing, this is called packing, and we can connect this member. So, this is the recommended configuration for pernils, and as I told that reverse direction we do not generally recommend. Now, for purlin design we need to know what are the load coming into picture. So, if we see for an example, say for channel section, if we see here that load is basically two type. One is the wind load which are acting perpendicular to the roof. We assume that winds are acting perpendicular to the roof H dash, and another is acting vertically downward, that is due to self weight, dead load, snow load, etc. This is P dash, right. So, the purlins are assumed, that means the codal provision says that we should design purlin as an continuous beam, because purlins are connected the truss members in different places and it is assumed as continuous beam. So, the moment can be calculated as P dash by P dash L by 10, where P dash is the gravity loads acting along VV direction. VV means this is the VV, right, and this is UU. So, P dash is the gravity loads acting along the VV axis, and which includes the sitting self weight of purlins, live load and snow load, right. So, M we can, the moment U we can calculate as P dash L by 10, where P dash can be written as horizontal load due to wind plus P cos theta, because if this is theta, this angle of inclination is theta, then we can consider this value as theta. So, the P dash value will become, so sorry, this is P. So, H plus P cos theta. Similarly, I can write the H dash value as P sin theta. This is basically the along UU axis. So, this will be along UU axis and this will be along VV axis, right. So, we can find out P dash as H plus P cos theta and H dash as P sin theta. Therefore, we can write mu as P dash L by 10 and mv as H dash L by 10, right. So, here P dash is basically the concentrated load at the center, or we can write that P dash into L, that means uniformly distributed load into L, total load. So, P dash is the total load, which we can also tell as P dash L. Similarly, H dash is the total load, which can be also written in terms of P sin theta means into L, if P is the uniformly distributed load. therefore, we can also write mu as H plus P, P is the uniformly distributed load, P cos theta into L square by 10 and mv is equal to P sin theta into L square by 10, right. So, or I can write H plus, means if it is concentrated load, then I can write total load into L by 10. So, in this way we can find out the moment acting on the member along UU and VV direction. And for biaxial moment, we need to check this interaction formula, that is mu by mdu plus mv by mdv should be less than or equal to 1, where mdu is the design bending moment about y axis and mdv is the design bending moment about vv axis. So, once we calculate the design bending moment about uu axis and vv axis, then I can find out the interaction formula and which needs to be less than 1. Now, question is how to find out the initial section size of a purlin member, because purlin is going to be act due to, means purlin is going to be withstand the load horizontally and vertically, and because of that the bending moment will come into picture in both the direction uu axis and vv axis, right. So, now we have to find out certain section size to start the design, and we do not know what should be the basis of the section size selection. So, here Gaylord et al. Gaylord in 1992 has made a formula where we can find out the plastic section modulus ZPZ as mz by fy by gamma m0 plus my by fy by gamma m0 into 2.5 into d by bf. So, approximate section modulus required for the section can be calculated from this formula, which is suggested by the Gaylord et al. In 1992. So, here mz is basically the factor bending moment about zz axis and my is the factor bending moment about y axis, and fy is the yield stress of the material, and d is the depth of the section and bf is the width of the section. So, considering this I can find out ZPZ. Now, again here you see, if we do not know the section size, then we do not know also d and bf. Okay. Again, if we have to know the d and bf, that means we have to know the section size. So, here it is a tricky, that how do I find out ZPZ unless I know the section size, I cannot know the value of d and bf, and if I do not know d and bf, then I cannot find out the ZPZ to find out an approximate section size. So, what we can do? We can assume certain d and bf at the initial, right, and we know for built up section for roll section what is the approximate bf and df value, d and bf ratio. Either we can consider certain ratio to start with and we can find out ZPZ value, or we can assume certain d and bf value and then on the basis of that we can find out ZPZ value. And once we find out ZPZ value, we can find out a particular section, say channel section or I section or angle section, whatever we need, and its size. So, once we know the size of the section, we can find out what is the d and what is the bf. So, after knowing this d and bf, we can find out what is the actual requirement ZPZ, okay, and whether it is satisfying that or not, right. So, in this way we can start the things, and it will be clear if we go through the steps what we need for design of the section. say for example, to design a channel section or I section is different the design procedure for angle section. So, first we will discuss about the design procedure of channel section or I section, and in case of channel or I section what we can start, that first we will find out what is the span length of the purlin, right. So, once we know the span length from the center to center distance of the adjacent trusses, then I can find out the gravity load, the total gravity load acting on the purlin P and wind load H, that we can compute, right. And the components of these loads in the direction parallel and perpendicular to the sheeting are determined. So, that means along UU and along VV axis we can determine the load, and these loads are basically service loads. These are multiplied with partial safety factor to find out the factor load, which the factor load, to find out the factor load we can find out the load factor in table 4 of the code for various load combination. So, after finding the factor load along UU and VV direction, that means parallel to the roof and perpendicular to the roof, once we find out the factor load, I can find out the maximum bending moment, that will be, that can be find out, that is P dash L by 10 or P dash L square by 10, right. So, maximum bending moment mz, or here we will say MUU, and similarly we can find out My or MVB, we say here MVB, and similarly maximum shear force Fz and Fy, right. So, maximum bending moment, shear force in different directions we can find out. After that we can find out the approximate section modulus required, that is ZP required, that will be calculated from this formula which was suggested by Gaylor in 1992, that is mz gamma m0 by Fy plus my gamma m0 by Fy into 2.5 into d by Bf, where my we know that factor bending moment about y axis. Similarly, mz is the factor bending moment about zz axis, Fy is the yield stress, gamma m0 is the partial safety factor for the material, which we generally take 1.1, and d is the depth of the trial section, and Bf is the width of the trial section. And I have told, to find out Zp required, we have to assume certain d and Bf, because here unknown is this as well as this. So, unless we assume certain things, we cannot find out the Zp required. Therefore, we preliminarily assume certain d and Bf, and then we will find out the approximate plastic section modulus required, right. And then next step, we will assume certain section size based on the ZPZ required, and then we will classify the section as per table 2, whether it is plastic or compact or semi compact. According to that, we have to then design, right. So, once we find this, then what we can do? We can find out the shear capacity of the section, say VDY and VDZ, right. So, VDY will be Fy by root 3 gamma m0 into AVy, and VDZ will be Fy by root 3 gamma m0 into AVZ, because here design shear strength has to be calculated for both the direction. That means, here we have to calculate and here we have to calculate. This is VDZ and this is VDY in this direction, right. And for calculating the shear capacity, we need to calculate the area, wave area, that is AVZ and AVY. AVZ will be d into TW that means depth, if this is depth and if this is the thickness of the wave, then d into T w will be the AVZ cross sectional area along ZZ direction, and AVY is the cross sectional area about YY direction, it is BF into TF into 2. This is the area BF into TF and in two side it is there. So, AVY will be calculated as AVY as 2 into BF into TF, where BF is the width of the flange, TF is the thickness of the flange, TW is the thickness of wave and D is the height of the section. So, from these dimensions we can find out the AVZ and AVY, and then we can find out the shear capacity of the section in Z axis and Y axis. Okay. Once this is done, we can now find out the design capacity in both the direction. Design capacity about ZZ direction MDZ can be found at ZPZ Fy by gamma m0, and it has to be less than or equal to 1.2 into ZDZ Fy by gamma m0. Similarly, MDY, the design capacity about YY axis, we can find out as ZPY Fy by gamma m0, and it has to be less than 1.2 into ZDY Fy by gamma m0. So, MDZ and MDY if we find, and this needless to mention that this MDY should be less than the MY value or MU, right, and this should be less than this should be greater than My, because this is design capacity and this is the external moment. Similarly, MDZ should be greater than the MZ, whatever moment is coming, right. So, that has to be checked. That means, we have to check that MZ is less than MDY, MDZ, and My should be less than MDY. Now, if it is not satisfying this criteria, then we have to increase the section size, and after increasing the section size, again we have to go through the same exercise. That means, we have to repeat the same and we have to find out again the design capacity of the section, both for shear and moment, right. So, unless this satisfy this criteria, we have to go on increasing, and if satisfies, then we can go for checking local capacity using interaction formula. So, interaction formula means that Mz by Mdz plus My by Mdy should be less than or equal to 1, because for biaxial bending moment we have to check the interaction formula and we have to fulfill this criteria. So, if this again if we see that Mz is less than Mdz and My is less than Mdy, but it is not satisfying, then again we have to increase the section size, because the biaxial bending moment, as biaxial bending moment is coming. So, we need to check for the interaction formula and we have to satisfy this criteria. So, once this is satisfied, then fine, otherwise we need to increase the section size and again we have to repeat, and once it is satisfied, then we will go for step 9, where we have to check for deflection and we have to check whether the deflection is under permissible limit. Okay. So, as per table 6, we have to check whether the deflection is under permissible limit or not, and if it is okay, then the section whatever we have considered is fine, otherwise we have to again redesign. So, this is how the channel section or I section for purlin member can be designed under biaxial bending moment. Okay. And we will be clear, means it will be easier to understand if we go through one example. Before going to that example, again I will discuss about the angle section, how to design a purlin using angle section. and in case of angle section we generally use some empirical relations to find out the angles, means section size of the angle section. So, let us see the steps which we use for this. So, for design of angle sections, but we will follow these steps, that is, first we will find out the vertical and wind loads which are acting on the truss member, on the roof truss. Then we will find out the value normal to this truss and parallel to this truss, right. Now, wind loads are assumed to be normal to roof truss and gravity loads are vertically downward. Then we can find out the maximum bending moment. Okay. Well, before that let me tell you that this vertical load also, for design of angle section we are assuming that that is normal to the roof truss, right. So, simply we are making approximate calculation. So, approximately we are assuming that all the loads are to be normal to the roof truss. So, if it is so, then we can find out mu value as simply W L square by 10 or W L by 10, right, where W is the uniformly distributed load and capital W is the concentrated load at center, right. So, maximum bending moment can be computed for angle section as this, small w into L square by 10 or capital W into L by 10, where small w into L is equal to capital W. Total load is equal to uniformly distributed load into length of the purlin. So, once we find out maximum bending moment, then we can find out the required section. So, for finding the required section, we can use this formula which is given by the code, where ZP required, the section plastic modulus, plastic section modulus will be m by 1.33 into 0.66 Fy. So, ZP required we can find out, right. Then we can assume certain relation, means the depth of the angle section we can assume 1 by 45 of the span and width as 1 by 60 of the span to start with a trial section of the angle for the purlin. Okay. So, the depth and width are assumed on the basis of 1 by 45 of the span and 1 by 60th of the span, and then with certain thickness of the angle section we have to arrive this ZP required. And you see, the depth and width must not be less than the specified values to ensure the deflection criteria. Okay. To ensure the deflection criteria, we should not make less than this the specified value. Okay. So, after that a suitable section now we can select to calculate the value of leg lengths of the angle section, and the modulus of section provided should be more than the modulus of section calculated. So, we have required section is this, and on the basis of assumed section we have calculated the section modulus which should be more than the required one. So, in this way one can decide the section size of the angle for purlin. Okay. So, this is how one can design the angle section. So, for purlin we have seen that generally we use either channel section, I section or angle section, and most commonly we use channel or angle. So, the design criteria for channel sections are discussed. Similarly, the design criteria, approximate design criteria for angle section to use as a purlin member are also discussed. So, on this basis the design of the members will be carried out. and in next class we will go through one example to understand how to design the purlin section. Thank you.